Welcome back. Now we have animation working for our character, and everything looks great. But Unreal Engine comes with some new features that are very, very useful, and so we're going to take advantage of those. Now, one problem that we can solve is an issue that we can see if we add some sloped geometry. So I'm going to take this platform here and hold Alt and drag another one out. So I'm duplicating it, and I'm going to go ahead and angle it a little bit upwards so we have a slope. And I'm going to bring this over out into the floor. And I'm going to duplicate it again so that we have a couple of these at varying slopes. So I'm going to turn off snapping for rotation and slope it down a bit. So we have a couple of different slopes. Now the reason I'm doing this is because our open world map is not flat, right? It has rolling hills. And if we're running along the rolling hills, we want to see what that's going to look like. So if we press play and run over to our slope, we see something less than desirable. We have our leg sticking out in the air. It's kind of like in the cartoons when the coyote runs off the cliff and hovers there in the air for a moment before he falls. But this time we're not falling, we're just kind of hovering here. And this doesn't look great. And in some games, it's kind of not noticeable. I mean, the older games do this and you kind of just ignore it. But modern games take this into account. And the way that we can account for this and fix it is by the use of Inverse Kinematics. So let's talk about it. Inverse Kinematics is a method that comes from robotics, but it's also used in animations quite frequently. And it's a method of solving equations so that we can move a particular bone on our skeleton. In robotics, you would move a particular piece of a robot. And this piece might be the end point on a robot arm. And a robot arm has joints on it, right? So if you want to control the end point, essentially the tip of the robot arm, you have to calculate how to position all of the joints up to that point on the robot. Inverse Kinematics, or IK, for animations in games works the same way. So imagine we have Echo here, and Echo is standing on the edge, and the left leg is sort of hovering there, and it doesn't look natural. And if we wanted this to look more natural, we would push Echo down until that left leg is on the ground and the right leg stays up. So that right leg sort of bends a little bit. This is more natural and looks better. Now we can use IK to achieve this. What we do is we push Echo down by a certain amount, and that left leg, which has these bones, if we look at that left image there, in red we have these bones, and as we push Echo down, we push that right foot up, and Inverse Kinematics solves the equations required to calculate where to put those other bones in the leg, how to bend them, where to put the knee, and so on. So IK is a more sophisticated way to take care of this problem. Now this involves some calculations, like how much do we push that leg up? So we have to figure out exactly where to move that foot bone and then take care of setting the transforms of those other bones in the leg. So here's a forward view of Echo with the leg hanging off to the side like this. Now we need to know how much to push Echo down. So that right leg, it's our left, but it's Echo's right? Now, if we push Echo down, we need to know how much, and we're going to go over the methodology here. So the first thing we do is we draw an imaginary sphere right there on that foot bone. And then we push that sphere down to the ground. We call this a sphere trace. Now, pushing the sphere to the ground actually doesn't take any time at all. It happens in the space of a single frame, and a sphere trace is capable of detecting hits. Notice the green circle on the floor. That means the sphere trace hit the floor, and the sphere trace can return the location at which the bottom part of that sphere hits the floor, so we can tell how far we traced. So we need to get this distance here, the distance until that trace gets a hit, essentially from the start point to the hit point. Now, we don't know which leg is hanging off as the game changes, and it could be one or the other at any point. So what we do is we perform two sphere traces, one on the left foot and one on the right. Now, in this case, the right leg, R left but echoes right, is the leg that has distance to the floor. Our other leg has a distance of 0 to the surface that it's touching, right? So for theoretical purposes, let's say that this point on the floor is 0 in the world Z coordinate axis system, and over here, the other leg has a Z location of 50. So there's this difference of 50 units that we need to push echo down by, and then raise that other leg back up. So here's the process. First, we do the sphere trace, and we calculate this offset between the foot and the surface beneath it. Now, we can call these Z offset L and Z offset R. And one of these is going to be smaller than the other, right? So we want to find which one is the lowest. So in this case, that sphere trace that went from echo's right foot down to the floor at Z equals 0, that one's going to have the lowest impact point for the sphere trace. So we're going to use that to determine this offset that we can move our pelvis bone down by. Our pelvis bone is at the hips, but all the other bones are attached to it. So if we move the pelvis down, the entire skeleton will move down. Now, once we've moved this pelvis down by this amount, our entire skeleton will move along with it, which means that leg that was touching the silver surface needs to be moved back up. And we need to use inverse kinematics to position all the other bones in that leg so that it's bending naturally. Now, when we do all this, we're moving bones. And if we move them instantly, this might result in snapping. So we want a more smooth movement. So we're going to use something called interpolation. When we interpolate, we move smoothly toward a target value. So that way we avoid snapping things and we get more natural movement. Now, inverse kinematics requires some sophisticated equations. If we have these bones in the leg and we need to move that foot up, then how do we position the other bones in the leg? We could position them this way and we'd still have our foot raised up, or we could position them this way and the foot is still raised up. In fact, there are an infinite number of solutions to this problem, which is why it's important to have constraints when it comes to being able to move these bones. And this is not an easy problem to solve, but luckily Unreal Engine has IK built into it. So we don't have to solve those equations. We just need to move that bone. Now we call that end bone the end effector. And the end effector is a term that comes from robotics, and it just means the bone that we're moving and all the other bones attached to it are going to move along with it according to those IK equations that get solved for us. Now, in order to do all this, we're going to create an asset designed for moving bones, and this asset is called a control rig. So let's hop into the engine and create our control rig for Echo. So we're back in the engine. We're going to open the content drawer, and here in Blueprints Character, we're going to make a new folder here, and we're going to call this Rigs. This is where we'll put our animation-related assets. Aside from the animation blueprint, I'd like to keep that next to /character. But in Rigs, we're going to make a new control rig. So let's right-click, go to Animation, and select Control Rig. And just like we did with our animation blueprint, it's asking for a parent class. We're just going to base this off of the base control rig class, as that's the only option here. And we're going to click Create. Now, we can name this CR for control rig underscore echo foot IK. So we have our echo foot IK control rig. Let's double click it and open it. And we have the rig graph. Now, this looks like an event graph. It's very, very similar. We can use this to perform calculations. Now, for our control rig, we need to specify a skeleton. Now, to the left, we have a viewport. And if we expand it, we have some tabs here. We have a My Blueprint tab where we can place functions and variables. And we're going to zoom straight over to the left where it says Rig Hierarchy. This is how we can get a skeleton here into our control rig. Now, before we do that, I'm going to point something out on our skeleton. So let's go back to BP/character, select our mesh, and in the details panel, we're going to browse to that mesh because that's the folder that contains the skeleton. We're going to double click the skeleton and open it up. Now, if you're following along with me and using Echo, we have some special bones on this skeleton that we can use in control rigs. They're known as IK bones. Now, these are bones that don't have any actual mesh geometry skin to them. They're sort of invisible there. Notice attached to the root, we have IK foot root. And attached to IK foot root, we have IK foot L and IK foot R. So these are IK bones. Again, they're not skinned to the mesh. If we moved the IK foot bone, it wouldn't change anything on the mesh. But we can use it for IK. Now, if you're using a different skeleton that doesn't have any IK bones, well, we can add something called virtual bones. So I'll show you how to do that, and you can use virtual bones instead of the IK bones that I'm going to use. Now, if you already do have IK foot bones, you don't need to do this, but I'm just going to show you anyway. To add a virtual bone, we first want a virtual root bone as a reference, and it'll take the same transform as our root bone, and then we'll have virtual left and right foot bones attached to it, just like our IK bones. We have these roots, right? So first we're going to take our root bone, the real bone, right-click on it, and we have Add Virtual Bone. And we can pick a target bone. We're going to pick the root, and now way down at the bottom, we have VB root root. So that's our new virtual bone, and it's based on the root bone. Now, we can right-click on our VB root root and add a virtual bone, but this time we're going to choose one of the feet. So we can search for foot and choose foot L, and now we have VB root root foot L. So it gives these kind of funny names, but we now have that virtual bone. And take a look. Here's what it looks like. This looks exactly like my IK foot L bone, as you'll see pretty soon. Now we're going to right-click on VB root root, add a virtual bone, and this time search for foot R, choose foot R, and now we have this virtual bone called VB root root foot R. Now we don't need VB root root, but I'm just going to leave these named as is, and now we have these virtual bones. So if you don't have the IK bones, use the virtual bones in place of them, and they can behave in exactly the same way. So anyway, we now know about IK bones, and if you don't have those, you can use virtual bones. So I'm going to close Echo Skeleton, and back to our control rig, CR Echo Foot IK, we can import a skeleton. So I'm going to click Import Hierarchy, and from the drop-down, we can choose a skeletal mesh. So let's pick Echo, or whatever skeletal mesh you're using, and we'll click OK. Now we can see Echo in the viewport, and the entire skeleton is highlighted, which is why we see all the bones. It's configured to show all selected bones. And you can change that by going to Character, Bones, and choosing how you want to see the bones. You can say None, All Hierarchy, which shows all of them like that, or the default is Selected Only, which is what I prefer. And clicking in the viewport will unselect or deselect them. So we have a hierarchy, and the control rig is going to allow us to change the bones, to manipulate them at runtime so we have more natural looking movement. We're simply going to do some foot IK, and we know that we need to do a sphere trace, right? So at any given point in time, one leg might be higher than another, so we're going to sphere trace from both legs straight down. And a sphere trace needs to know a start point and an end point for the trace. And what we can do is take one of our foot bones, either the IK or the virtual bone, and trace starting a little bit higher and ending a little bit lower. So we're tracing with a sphere from just above the foot down to below the foot by a certain amount. And to do that, we want a function to handle this. So we can go back into the My Blueprint panel and make a function for this. So we're going to go to the functions and click plus to make a new function. And I'm going to call this function foot trace. So foot trace is going to perform this line trace. And we can add input parameters to this function by clicking the entry node. And in the details panel, we have inputs. We can click plus to add a new one. Now the type for this is going to be rig element key. And select rig element key and rename this to IK footbone. Now a rig element key is a data structure that has a type and a name. Now type is color-coded green. That's the color coding for enums. So there's an enum that we can use to specify this type. And there are several types in this enum to choose from, like bones and so on. Now, here's what we're going to do. We're going to right-click in the graph and type get transform and select that. Now, notice get transform has input parameters. So this node is designed to get the transform of something. Now notice we have type and name here. Type is the enum, and if we click the drop down, we see all of the constants possible for this enum. There's none, bone, null, control, curve, and reference. Now we're concerned with bones, but we don't have to just plug in a type and a name because look, this is actually an input item. So expanding the drop down shows all the stuff that item contains, but we can simply take the input that was passed into this function when it was called. We haven't called it yet, but we will, and we'll pass stuff into it. And when we do, it'll be available here. And we have the IK footbone passed in. So we're going to take that light blue IK footbone, the rig element key, and hook it up to get transform bone. So now item will contain the type and the name contained in that IK footbone input parameter that we'll pass in. Now, we want this in global space. We're going to be working in global space here. There's local space as well, but we want global. Now, get transform bone returns a transform. But notice that many of these inputs have drop downs, and so do the outputs like transform. And if you expand it, you can expand the transform struct, which contains a rotation, a translation, and a scale 3D in control rigs. So we have the transform for the bone, right? And we want to do a sphere trace from just above the bone to just below the bone. And in fact, I'd like to go a little bit to the side of the bone as well. So that way we won't be tracing down and hitting the foot itself. We want to trace down to the floor. So what we can do is take our translation and hit the drop down to expand it to its X, Y, and Z. And we can take the Y and add to it. So we're going to click and drag off and type add. And here in control rigs, we have various types of ways to add. We want add float that looks like this. It's a blueprint pure function, right? And we're going to add simply the value 5 to it. So we're moving over by 5. So we've moved it over by the Y just a bit. Now what we're going to do is we're going to do our sphere trace. Now there's a function for that. It's called sphere trace by trace channel. And we can trace against certain trace channels. Now, these trace channels are built into the engine, and we'll talk a lot more about them later. But when we do traces, we typically trace against the visibility channel because almost all objects are configured to block the visibility channel. That just means whenever traces are performed and they're using the visibility channel, they'll actually hit things that are configured to block the visibility channel. And our trace needs a start point and an end point. Now we have our foot bone, and I mentioned we want to raise it up. So what I want to do is right click and use add and get an add vector node. And it takes A and B as inputs. These are vectors, and it returns the result, which is these two vectors added together. Now we can expand A and B and specify X, Y, and Z for these two vectors. Now this is going to be the start for sphere trace by channel. So I'm going to hook that up to start. And what are we going to add? Well, first I want to take my foot transform, but I do want this 5 added to its y. So I'm going to drag in x straight to the x for a. I'm going to drag in the result of this add for y because we're adding 5 to the y. And I'm going to hook z in for the z. Now, what am I adding to this vector? Well, I'd like to add a vector straight up in the z direction with a length of 50. So I'm just going to add this hard-coded xyz set of components, 0, 0, 50. So this gives me a starting point at the transform of the foot bone, but raised up by 50, and of course pushed over by 5. So that's my start point. But what about the end point? Well, I want to take my foot bone and push it down by about 50 or maybe 100. So I'm going to right-click and get a subtract, and it's going to be subtract vector. And I'm going to expand these here, and I'm going to use the same x, y, and z that I use for my add node. So I can get my x from there, I can get my y from the add node, and I can get my z from that bone transform. And what am I subtracting? Well, I'd like to subtract a vector with 0, 0, 100. So this location is below the foot by 100 units. So I'm going to stick that into the sphere trace endpoint. And the sphere has a radius. This doesn't need to be a big sphere. We can set the radius to about 3. So this is a small sphere. Now this function is performing a line trace, and we can simply return the hit point. So I'm going to click on my return node and add an output to it by clicking plus under outputs, and I'm going to change this to a vector output and call this hit point. And I'm going to take my sphere trace, which, look at this, it returns a hit location. It returns some other information too, but the hit location is what I'm interested in. That's what I'd like to return from this function. So now we have a function that performs our sphere trace, and we're going to use this for both the left and the right feet. So that's going to be our next step. So back to our graph. Now, before we do this trace, I'd like to have a Boolean variable on my control rig. And I can check this Boolean and only trace if it's true. That gives me more control later on. So I'm going to click plus add in the My Blueprint panel, add a variable, and call this should do IK trace. And if I drag this out and get it, I have my should do IK trace Boolean, and I can get a branch. Now a branch is just like an if statement. It checks the Boolean and executes either the true or false output execution pins based on the value of the Boolean. So if the Boolean is true, I want to do the sphere trace. So I'm going to call foot trace. Now, what do I pass in for IK foot trace? Well, we can expand the dropdown, and we can choose the type and the name. So for the type, I want to choose bone, and for the name, I want to use my IK foot bone. I want to use IK foot L. Now, if you're using a mesh that doesn't have IK bones, you're going to use those virtual bones instead. But I have IK bones, so I'm going to use IK foot L. And again, it's just a bone, and it's at the same location as the foot. Now, we're going to see why we're using the IK bone instead of the foot bone. That's because we can move the IK bone, and the mesh won't go with it. And then after we perform some calculations, we can start moving the actual bone. So now that we're performing a line trace, I'd like to store the Z of that hit point. And look, we can expand the output called hit point. So I'd like to store that Z, and we're going to be storing this for both feet. So I'm going to drag off of this and promote it to a variable. And in the My Blueprint panel, I'm going to rename it to Z offset underscore L target. So target indicates that we're going to want to move our foot towards it, right? So we have this Z offset L target, but we also want one for the right foot. So we're going to call foot trace again for the other foot. So let's do foot trace. And this time we're going to expand the input IK foot bone and choose bone for the type. And I'm going to use the other IK bone, IK foot R. And again, if you're using virtual bones, use your virtual right foot bone. And we're going to expand hit point and promote this z to a variable and call this one z offset underscore r target. And we're going to hook that on up. So now we have these targets, right? But we are checking a branch to see if we should do an IK trace or not. And if that ever becomes false, say in the middle of the game, we should reset these z offset targets to 0. So we're going to get z offset L target and set it, and we'll leave that value at 0. And z offset R target, we'll set that to 0 as well if should do IK trace is false. Now I know this seems very abstract right now, but all we're doing is doing the trace and getting the z for those hit points for the sphere trace. And that's step 1. That's the first thing we need to do. Now step 2 is to do that interpolation thing I was talking about. You see, we have these target variables, but we're going to have some actual variables, not targets, but the actual z offsets, and we're going to interpolate them smoothly towards our target values. So in addition to z offset right and left target, we're going to have a couple more floats called z offset L and z offset R. So let's make those. So I'm going to make one called z offset underscore L and change its type to a float, and make another one called z offset underscore R. And we're going to interpolate these values smoothly towards the targets. And this allows us to use these z offset L and R when we move our pelvis down and move the feet up later. We'll be using these values, which we're going to interpolate. And I'll show you how. So we need to do more stuff. And if we keep dragging off of these pins and adding more nodes and dragging off and adding nodes, we're going to have this big, long line of nodes. So instead of doing that, there's a nice way in Blueprints to organize these, and that's with a sequence node. So I'm going to drag off the forward solve and get a sequence. Now, by the way, forward solve is kind of a strange name for an event, right? Usually we have like tick or begin play. Well, forward solve is constantly updating like tick, but we don't have delta time as an input for it. And you might be thinking forward solve, maybe that implies there's a backward solve. And there is, and we're not going to get that deep into control rigs in this video, but it's enough for now for you to understand that forward solve is constantly updating, just like the tick function. Now the sequence has A, B, C, and D, and this is how it works. First, it executes A, so it's going to go through all these nodes, and once those are done, then it starts B, and once those are done, it starts C, and then D. So that's how it works. So we have A, right? And that's going to be our step 1. And we can comment this just like we do in C++. We can highlight these, hit C, and I'm going to add a comment for this. And the comment is going to say 1, sphere trace from feet to ground. So that's step 1. And now we're going to do step 2. Notice I can move all the nodes at the same time by moving the comment, which is nice. So that's step 1. Now step 2 is to do the interpolation, and here's how. We take our targets, right? These targets are the z values of our trace, wherever our trace hit. So imagine for a second that one of these legs is up in the air like in our diagram earlier, and we trace down to the floor by, say, 50 units. Well, when we hit the floor, we just stored the z of that location. And we're going to use this as a target to interpolate our z offset L towards. So here's the variable we're interpolating towards z offset target. And here's how. We can drag off of the value of z offset target and type alpha interpolate. And we want alpha interpolate float. Now all that this does is returns a float value. It takes our value we passed in as the target and returns us a value closer to that. How close? Well, that depends on interp speeds. So we have interp speed increasing and decreasing. That just means how fast do we start approaching and how fast do we settle into the final value. We're going to set these both at 15 and take our result and set our z offset L. So we don't actually need a getter for that. We need a setter. So we're going to set z offset L to the result of the interpolation. That's going to be plugged into B. And after doing L, we need to do R. So we're going to get Z offset R target, drag off and alpha interpolate using the float version. And we're going to set our Z offset R to the result of that. And we're also going to use 15 and 15 for those interp speeds and hook that up. So that's the next thing we do. So let's comment this and say 2. I'll zoom in so you can see. I'm going to say interpolate smoothly toward offset targets. So basically we have these Z offset L and R variables. And as our targets change, Z offset L and R are going to follow them, but smoothly, right? They're not going to follow exactly. They're going to sort of tag behind a little bit. And for both of these, we're going to want to check interp result. That way we'll actually have interpolation. Now, I mentioned that we need to find out which one of these is the lowest, right? Which one of these targets is below the other. And that's the one we're going to use as the target to move our pelvis down. We need to determine which one is lower. So we're going to get our variables. We're going to get Z offset L, we'll get that, and Z offset R, we'll get that. And to determine which one is lower, we're going to use a less node, less float. This returns a Boolean. And we're going to check this with an if. Now, this is interesting. Blueprints have branches which behave like if statements, but control rigs have if nodes. And here's how they work. First, let's take our Z offset L and R. I'm going to highlight them both, and Control D, that's going to duplicate them. And I'm going to drag off of Z offset L and type if. And if I select if, check this out. It takes 2 floats, and it takes a Boolean. Here's how it works. If the Boolean is true, it outputs whatever we plugged into true. So Z offset L. And if the input Boolean is false, it outputs whatever we plugged into false. So here's how all this works. We're going to hook up the less into the if, and less is going to see is Z offset L less than Z offset R. If so, it's going to return true, which means the if will return Z offset L, the lowest one. But if Z offset L is not lower than Z offset R, less will return false, which means if will return Z offset R, which is the lowest one. So regardless of which one's lower, the result here is going to be the lowest target point. And that's going to be what we use to offset our pelvis. So we're going to make another variable. It's going to be a float, and we're going to call this Z offset underscore pelvis. And we're going to set it to the result of this. So this calculates the offset for our pelvis. And we want the lowest point to prevent ourselves from trying to overextend. So we're going to make a comment here that says 3, use the lowest foot offset to prevent overextension. So that's part 3. So we have these variables that we went through all this trouble to calculate. How exactly do we use them? Well, what we're going to do is use them to transform our IK bones, or if you're using virtual bones, your virtual bones. We're going to transform those. We're essentially going to change their Z values to our variables that we calculated. Now remember, these are moving around smoothly. They're not snapping anywhere. So we're going to transform our virtual bones to use these for the Z values of their locations. And remember what these are. These are the points, at least in the Z axis, on the ground. These are the Z coordinates where our sphere traces went straight to the ground. So if we're moving our bones straight down to the ground like that, in a smooth manner, then the only thing left to do is to transform our actual bones. Now, why aren't we doing it to the actual bones directly? Well, because we need IK, right? If we're moving one of our legs up, we need to make sure to take care of the other bones in a graceful manner. That's where IK comes in. So we're almost there. First, we need to move our virtual bones or our IK bones, whichever you're using. So that's going to be the next thing we do here. And to do that, we're going to right-click and type Modify Transforms. Now, Modify Transforms has an array element here. See the 0? It actually has an input parameter of type array, and it's an array of items to modify. And if we expand the first element, we see that we can choose its type. We're going to leave it at bone, and we're going to transform the IK foot L bone. Or, of course, if you're using virtual bones, you're going to use your virtual left foot bone. And we're going to change its transform, but not the whole thing, just its Z location. So we can expand the transform, expand translation, and we just want to change its Z location to that point we traced to. So, since this is the left foot, we're going to get our Z offset L and plug it in to the Z here. Now, we don't want to change anything else. So what we're going to do is set the mode here to additive global. Remember, we're working in global space, and additive global means add these values to the transform. So we're basically adding a whole bunch of zeros to the transform, except for the Z. So we're going to take that offset and add it to this IK foot L bone. So I'm going to hook this up to the C part of our sequence. And we just did the left bone. We need to do the right bone as well. So let's do another modify transforms. So modify transforms. We're going to expand that 0 element and change the name. And I'm going to use IK foot R this time. And of course, you'd use the virtual bone if you're using those. And I'm going to expand the transform, expand translation, and this time use Z offset R. We're going to add that offset and change this to additive global. Okay, so what we've done is moved our virtual bones. We also want to move our actual body. And we're going to do that by moving the pelvis. So I'm going to right-click, modify transforms, and for this one, expand that 0 element and choose the actual pelvis bone. So this is not a virtual bone here. Over here, we're moving virtual bones, or IK bones. That's an invisible thing. We wouldn't actually see the mesh change by moving these, but the pelvis is another story. This is a real skinned bone. If we move this down, we're moving the whole body down because everything will follow the pelvis. We're going to move the pelvis in the Z direction. And that's why we calculated Z offset pelvis, which is really just the lowest of the two offsets that we got from our sphere traces, right? We're only moving by the lowest offset. And this too is going to be additive global. Oops, I selected override global and my character went sideways. I want additive global. That's better. See, this is executed constantly, even while the game is not running. So you can see the results of it if you do something wrong, right? So that's kind of useful. I'm going to leave it at additive global like it should be, and we'll comment this, and this is step 4, so we're going to say for add the interpolated offsets to the IK foot bones. If you're using virtual bones, you're going to say VB foot bones. This will move them up or down. So that's step 4. We moved our virtual bones, and of course we moved our actual pelvis as well. Okay, that's step 4. We're almost done. The next thing to do is take care of that IK. And Unreal Engine 5 introduces something called full body IK. Full body IK is interesting. It allows us to do IK on really any chain of bones on the body. So we can specify end effectors. We call them effectors here. Basically, what bone are we moving? And it's going to move the rest of the body naturally. So this does a lot of work for us. Now, it's asking for a root. Our root is the pelvis. The pelvis bone moves, everything else moves with it. And it's an actual bone here on the body. The root bone isn't skinned to anything. The pelvis is behaving like our root for full body IK. And we're going to hook this up to our last part of the sequence, that D part. And for our effectors, we can add elements. Now, we could pass an array in, but we don't have an array to pass in. We're going to hard code it, right? We're going to click plus and give it an element. Now, here are all the fields of one of the elements. It has a bone. We're going to select the actual bone we're moving now. So we're actually moving things now, not just virtual or IK bones. We're going to choose the foot L bone. This is the actual foot L on the body. And you can see it's already starting to get wonky, right? Because we haven't passed in how to move it, right? We want to give it a transform to move this bone to. So we want the transform of the IK bone or virtual bone if you're using those. So I'm going to get a transform. We're going to use get transform. And for the transform, we want the type to be bone. And we're going to use the IK foot L bone or virtual bone if you're using virtual bones. And I'm going to plug that into transform, right? And things go back to normal here. And that's because, well, when we do our line trace, we're already on the floor, so we're not really moving that IK bone at all. We'll see it, though, when we start playing in the actual game. Now, here's the beauty of full body IK. We can add more effectors. We could add any effectors on the body. We're going to add another one for the right foot. So let's click plus, and now we have element 1. Now for the bone, we have to select it. We're going to choose foot R, the actual right foot. And look, it goes all wonky. But we're going to use get transform. And for the type, we use bone. And for the name, we're going to use that IK foot R or VB foot R. But I'm using IK. So that goes back to normal once I plug that in. So full body IK is going to make sure that when we're moving our feet, then the legs will be bent naturally. So let's compile this. And now the only thing left to do is to actually use this. Actually, let's comment this last part. We're going to comment this and say step 5, right? And this is going to say use full body IK node to solve IK and use the IK foot bones as the effector targets for each foot. All right, that's exactly what we're doing. So before we actually start using this, I'd like to sort of recap and go back and talk about what we did. So first we made a Boolean. We're going to see very soon where we can set that. And if it's true, we're doing a sphere trace. We're tracing from above the foot down to below it, and wherever we hit the floor, that's going to be the hit point. We're only concerned with the Z for that, and we're saving that as Z offset L target. That's for the left foot, and we have one for the right foot. Okay, so we have these Z offset values. They're the Z coordinates for the hit point for our sphere trace. Next thing we do is we take our Z offset variable and smoothly move it towards that target. That's what we got from our sphere trace. So we're actually using the Z offset L, but we're smoothly moving it towards the target that we got from our line trace constantly. We're doing the same for the right as well. And then we see which one of these is less, which one of these is the lower value, right? Not the smaller absolute value, but the lower in Z space, lower towards the center of the earth. And we're taking that and using that one for our pelvis. So we're moving our pelvis down so that we're always going to have both feet on the ground. Basically, the whole body will be lowered down once we actually use this. So we have the Z offset pelvis. After that, we transform our IK bones or virtual bones. We're adding to them. What are we adding? Well, we're adding this Z offset. So we do that for left and right and the pelvis. So we're adding to these values, and then step 5, we use full body IK. And we're moving the left and right feet to the transforms of our IK bones. And full body IK does this in such a nice way that it's going to bend the other bones in the correct way. So we now need to use this thing. And we use this in the animation blueprint. So let's go back to ABP Echo all the way out to the anim graph. And just before our final output pose, we're going to right click and type control rig. and we have a control rig node, and we're going to drive our pose straight through it. And control rig allows us to set the control rig class. If we scroll down, we have control rig class, and if we drop the drop down, we can search for CR echo foot IK. We're going to use that. Now, remember that Boolean? If we go back and select should do IK trace and click this eye icon so it's visible or public, we can compile, and back in ABP echo with control rig selected, we can now see should do IK trace. And if we check that, this should do IK trace use pin, we now have a pin here and we can plug in a Boolean value. Isn't that great? So at first, I'm just going to check it. So it's basically passing true in by default. Let's see what happens if we do that. Let's go ahead and compile, hit play, and well, that doesn't look so good. We don't want that, right? But if we move up to a slope, it looks funny, but if we move up to a slope, at least the legs are going down to where they should go. But yeah, this doesn't look great when we're moving, right? Now let's expand the settings here, and we're going to want to configure this. Now, number of iterations means how many calculations are we going to let this do before it comes up with a solution. We can leave these all at their defaults, but the root behavior though, if we hover over it, says set the behavior of the solver root. Pre-pool translates the root and all children by the average motion of the stretched effectors to help achieve faster convergence when reaching far. But what we need is pin to input, which locks the translation and rotation of the root bone to the input pose. The input pose being the pose before we did all these transformations. That's what we want because we're only changing the specified bones. We don't want to change the root in any other way. We're going to leave that at pin to input. So when should we do the line trace? Well, we should do the line trace when we're definitely not in the air. So we can take is falling and get a not Boolean and hook that in. That's a pretty good condition. But also we don't want to do our control rig at all if we're running, right? Because let's just see how this looks when we're running, right? So if we're running, well, look at that. We're forcing both legs to be on the floor and looks like we're kind of ice skating. Now, if we go up to a slope, we do get the behavior we want, right? This does look really, really good when we're standing still, but we don't want this behavior when we're running. That doesn't look good. So there's a way to have a sort of if statement, kind of like a branch here, where we use one pose based on a condition or another pose if that condition is false. The node to do that is called blend poses by bool. Blend poses by bool takes a Boolean. So what do we want to use for our Boolean? Well, if our ground speed is 0, so we can say double equals 0 and plug that in. And here's how it works. If ground speed is 0, then blend poses by bool will return whatever we plug in to true. And if ground speed is not 0, it'll return whatever we plug in to false. So it works a lot like that if in our control rig. Now, if ground speed is 0, we want to use our control rig. So we're going to plug that in. But if it's not 0, we don't want to use our control rig. We just want our main states. Now, we can't just copy it. We want to cache the pose. Remember, we can cache poses. That's a better way to do it. So we're going to take main states, drag off, cache the pose, call this cached pose main states, and now we can use that instead. So we want to use it both for the control rig, so use cached pose main states here, and this we can copy. So we're going to copy that and use it for the false pose. Okay, so that was a lot of work, but if we compile and test this, we're going to see how much it pays off. So we're running, everything looks great. We stop on a slope, and we have foot IK. And we can really see it when we're stepping up on a ledge like this. So this is a huge improvement. This is going to come in really handy in our rolling hills for our open world map. So that'll be something good to test it out on. But check this out. Doesn't this look great? And of course, we can alter the parameters, maybe change our sphere trace so it doesn't go down so far, because really, I mean, you may not want your leg to go up this far on a table, but I leave that to you as an exercise. Tweak the parameters, get it looking how you want it. Perhaps post some screenshots in the Discord, see what other people think, show off your work, and congratulations, this was a big lesson. And it kind of had to be, right? This is one big thing, the control rig and leg IK, it all goes together. And I know that this was a long video, which is why this is optional. But if you stuck through it and you achieved foot IK, congratulations, because this is a really nice feature that really only the newer games use. And when it's done, you notice it and it really looks great. So really good job. Congratulations. I'm very proud of you for sticking through this. And now your character has amazing looking leg IK. I'll see you in the next lecture.